Okay, then let's quickly start our class. It's already late. Okay. Is my screen visible?
Yes, ma'am.
Okay, thank you. Okay, so last class we were doing about the screening of your wastewater. So we have learned about the screening process. So screening process is what that it retains your all your suspended particles like your wood blocks or dead animals or whatever suspended particles are there. So it retains all those things. Okay. So again, we have learned there are different types of screen. That is your fine screens, medium screens, then your movable screen is there. Okay. So all those things we have learned in our next last class. So now today, after your screening process, it is same like your this is your like raw water. For raw water, what we have done our sedimentation process. But here, before our sedimentation treatment part, we will for your wastewater treatment, we will be doing after your screening, we will be doing a grit removal process. Okay, and that is done in your grit removal basin. Also, it is known as your grit chamber, or you can say it as your grid channels, or also as your detritus tank. Okay, so all these four names are same, doing the same thing. So these are, these grid removal basins or the grid chambers, they are placed, before the in front of this wastewater treatment plant, and they are, type of this sedimentation basins only. They are actually the type of sedimentation basins, and they are placed in front of this wastewater treatment plant, and they remove what? They remove the inorganic solids or the inorganic particles. Inorganic particles act as of what? Like your, you can say in the wastewater, there will be sands, okay, there will be gravels, there will be grit. Again, there can be any non-putrescible materials, all those things which, they may clog the channels, or there is a chance that they damage the pumps. Okay, so all those things, they are, removed by this grit removal basins. So basically it's your sand, gravel, grits, all those things, it is being removed, and they, so that they cannot, clog the channels further, and they do not damage the pumps, and also to prevent their accumulation in the sludge digesters. For that reason, grit removal basins are used. Okay, then uh, then we come to, okay, so next we come to our, there is actually a theory behind your settling, whatever settling is being happening there in a grid removal basin, and this one. So there is, there are some theory behind that. Okay, so basically this sedimentation, we know that sedimentation, basically it is a process, to separate the suspended material from a water, or from, you can say, from this wastewater also, by the action of what? By the action of gravity. Okay, so since we are keeping it in a still position, and this suspended particles, these grits or whatever it is, so the suspended particles, it just settles down under the action of gravity. So the gravity is the main factor here happening in your sedimentation process. Okay, so basically, there is a principle behind this, the behind the process of this sedimentation, and it is that, that this organic matter, whatever organic matter is present in the sewage, it is having a specific gravity, greater than water. Okay, water specific gravity is one, we everybody know. So the what is happening here in this wastewater is that, the organic matter whichever is present in this wastewater or in the water also. So these are having specific gravities, greater than water, that is, you can say 1. So when you keep the sewage in a still position or in a fixed position, when you keep it so for many hours, so what happens, so these particles or these organic matters, these will tend to settle down. Obviously they will settle down by, because there is gravity, because of the action of gravity they will settle down, and also because your specific gravities are greater than that of this water. Okay, so on the other hand, if the sewage it is flowing, okay, it is not in a still position, so what will happen, they are these organic matters, they remain in suspension. Okay, since the sewage is flowing, the sewage is in motion, so also these organic matters, they will remain in suspension because of the turbulence happening in the water. Okay, so but as soon as this turbulence, if it is stopped, or it is retarded, okay, when you give some storage, when you provide some storage to this sewage, as to the turbulence in the water or the wastewater, it will be retarded. So these impurities, that only in that case, these impurities, they will tend to settle down at this bottom of the tank. Okay, and this is the main principle behind the sedimentation process. So this is the same like whatever we have learned in our raw water engineering also. Okay, so now if you are going to design a sedimentation basin, so the first important thing is it will be dependent upon the settling velocity of the solids, or you can say the sewage solids. So the main thing, the design of the sedimentation basin is dependent, it is on the settling velocity. So first we have to know the different settling velocities of the of the sewage or of the wastewater. For that also, we have different type of theories. We have some theories for the settling, and this type of settling, it is known as your type 1 settling. Okay, so whatever settling is happening here, it is known as your type 1 settling. So it is the theories, there are different theories of type 1 settling happening. So the first factor or the first theory is like the velocity of the flow, the velocity of the flow, like which carries the particle horizontally. So the flow is happening horizontally, so what is the velocity of the water, or what is the velocity of the wastewater, it is on which the particle it is carrying. Okay, so if the flow area will be greater, okay, so the if the flow area of the the whole sedimentation basin or the grid basins, it will be large, then what will happen, the velocity will be, obviously it will be less. Okay, and if the velocity is less, then what will happen, the particle will settle down more easily. Okay, so this is the simple theory behind your type 1 settling. The next theory is like the viscosity of the water. Okay, so what is the viscosity of the water in which the particle it is traveling? So we know that the viscosity, it is it is varying inversely with the temperature. Okay, so viscosity, it is varying inversely with the temperature. Let me wait, just wait. Let me. The meeting is locked. Students are waiting. Okay, so we know that the viscosity, it is inversely it is varying with the temperature. So if the water is warm, or if the water it is hot, then the water it is less viscous. Okay, so if the water it is less viscous, then obviously it will provide less resistance to the settlement. Okay, it is just the inverse one. So this temperature of this water, it cannot be controlled by any it cannot be controlled, the temperature it cannot be controlled to any extent. So the main thing is that the viscosity, it is varying inversely with the temperature. So if the water is less viscous, so if the water is, sorry, if the water is warm or it is hot, then it is less viscous and it will obviously offer less resistance to the settlement. The third the third theory is the size, shape, and the specific gravity of the particle. So obviously, if the if the specific gravity is more, then what will happen? The particle, it will settle down very easily. Okay. If the particle size is more than if the specific gravity is more than the particle, it will settle down very easily. Okay. And there is one settling velocity. Your Stokes law equation is there. So you can see here in the screen, you can see. So this one, actually there are different types of expressions for your settling velocity, and it is same like that of your whatever we have done on our treatment of water part. So this is, first one is your Stokes law. Okay, so this equation, Vs is equal to G by 18 G minus 1 d square by nu, and this equation is only for the particle size, that is the diameter of the particle size, it will be less than 0.1 mm. Okay, if the diameter of the particle size, it is less than 0.1 mm, in that case only you can use this equation. Okay, so in this equation, also here the Reynolds number, it is less than 0.5. That means it is for very small size particles. Okay, so here this Vs, it is a settling velocity, known as a settling velocity, which is in your meter per second. Then d is obviously the diameter of the particle, and that is in meter. And your capital G is your specific gravity of the particle. Then nu is your kinematic viscosity, and unit is your meter square per second. Then comes your Re, that is your Reynolds number. Okay, so basically, this equation is known as your Stokes law, is given by Stokes law, and it is based on when the particle size d is your less than 0.1 mm. So it is a expression of your settling velocity. So next is your derivation is not needed. Okay, so next one is your if what the when the settling velocity, or sorry, if the diameter of the particle, it is like it is lying between 0.1 mm, it is lying between it is lying between 0.1 mm and 1 mm. Okay, 0.1 millimeter and 1 millimeter. If the particle size is lying, then you will be using this equation. Okay, Vs is equal to G, capital G minus 1 by 13.88, D to the power 1.6 by nu to the power 0.6 and whole to the power 0.714. So this is your equation for when D is lying between 0.1 mm and 1 mm. So next one is your, like for turbulent settling also you can say, when the diameter of the particle size, it is greater than 1 mm. So this equation you will be using this one. Okay, Vs is equal to 1.8 root over Gd G minus 1. So this is your equation for D is greater than 1 mm, and this equation, it is given by Newton. Okay, it is given by Newton's equation for turbulent settling. This equation is known as. Okay, so these three equations you have got for your settling velocity. So okay, another equation is there. Another equation is there. This one is known as your modified Hazen's equation for transition zone. So if it is in transition zone, like I told you, like if the particles are between 0.1 and 1 mm, another form of another, like Hazen gave another equation, that is your this one. Okay, this one is another equation you can use for when the particle size is lying between 0.1 and 1 mm. Okay. Now coming to the grid chambers and the grid channels. So already I told you that the grid chambers, they are the sedimentation basins, and they are placed before the, in front of the wastewater treatment plant. And as sometimes these are usually, again, these are after the fine screens before. I mean, if the screening is done, after that the grid chambers are provided. And after grid chambers, your sedimentation process is there. So after the fine screens, or after the screening process and before the sedimentation tank, the grid chambers are provided. And these grid chambers, we already told that they remove the inorganic solids, like what, like the grids, the sands, the debris. So all those things they remove. Okay, the sand, then your non-putrescible things. Okay, so all those things they remove. And this the some grits, the amount of grit that is collected, it is of some, there is some range. So what is the grit quantity that may be vary? It is between 0.004 to 0.037 meter cube per 1000 meter cube of sewage for separate sewerage system. You can see this line. These things you can note it down in your copy for your numerical purpose. Okay. So all these things you see, the grid quantity, it may vary between 0.004 to 0.037 meter cube per 1000 meter cube of sewage for separate sewage system, while this may range between 0.004 to 0.180 meter cube per 1000 meter cube for combined sewage system. So if you can remember, we have learned about the types of sewage system in your fifth semester. There is combined sewage system, there is separate sewage system, there is partially combined sewage system, if you can remember. Okay, so for those different types of sewage systems, the grid quantity, that is different. Okay, so again, these grid chambers or those grid channels, they are designed to remove the particles having the specific gravity that is greater than 2.65. Okay, and they should have a nominal diameter of 0.20 mm, and they have a settling velocity of about 21 millimeter per second at 10 degrees Celsius. So this is the like the minimum consideration, or the thing which should be there for a particle size, for a grid chamber to be designed. So a grid chamber, uh, if you are designing a grid chamber, so it should be the particle size, it should have a specific gravity greater than 2.65, then it should have a nominal diameter of 0.20 mm, and also it should have a settling velocity of about 21 millimeter per second at 10 degree Celsius. Okay, so now we have different two types of, you can say, two types of your grid channels or grid chambers. So one is your horizontal flow, that which is a non-aerated one. So a horizontal flow type, and the other one is your aerated flow type. Okay, so we have two types of grid channels. So in the horizontal flow type of this grid channel, what happens? The flow, it passes in a horizontal direction through the channel. Okay, so in the horizontal flow type, the main thing is that the flow is happening in a horizontal direction through the channel. Okay, then coming to the the constant there in the horizontal this flow type, that is your aerated one. sorry, non-aerated one. So what is happening here? There is a constant velocity is there. Okay. So this constant velocity, it is achieved by providing some control sections. Okay, it is provided by providing some control sections, such as what, such as a proportional flow where at the affluent end of the rectangular channel. So if there is a rectangular channel, so at the end of the rectangular channel, so there is a proportional flow where is there to control the or to achieve the constant velocity of the channel. Okay. Now the next one is your the aerated type of grid channel. So this aerated type of grid channel, there is a spiral. It is a kind of a spiral flow aeration tank. So there is a spiral type of thing. So where there is a spiral velocity, and it is the spiral velocity. It is controlled by the dimensions of the chamber. Okay, so basically there is a, it is a type of consist of a spiral type of flow velocity thing is there, and that is happening, your spiral velocity is there, which is controlled by the dimensions of the chamber. So next one is your, okay, next one, let me see. Okay, so we can do one numerical now. Okay, we can do one numerical before proceeding to the next topic. So in this numerical, while doing the numerical, actually there are different types of design. Since this is a design problem, so there are some values which you need to remember. Okay, which are fixed values which you need to remember. So let us first see this numerical. Okay. So this numerical says, like it is written as, a rectangular grid chamber. It is designed to remove particles with a diameter of 0.2 millimeter, and specific gravity is 2.65. Settling velocity for these particles has been found to range from 0.016 to 0.022 meter per second, depending on their shape factor. So a flow through velocity of 0.3 meter per second will be maintained by proportioning where determine the channel dimensions for a maximum wastewater of 10,000 cubic meter per day. So here what things are first given, let us see. So here it is, they are talking about a rectangular channel, and they are providing a proportional wear, okay, for controlling what? For controlling the velocity of the flow. So just now we have learned the proportional flow wear is provided to maintain the velocity of the flow. So there, so what is the first one is given? What is the horizontal velocity? Okay, what is the horizontal velocity that is given here? You see question. It is 0.3 meter per second. So they have written the value. Okay, horizontal velocity of flow, it is your 0.3 meter per second. So now next one is your, like, what is the settling velocity range given to you? It is 0.016 to 0.022. So that one they have written. Okay, and since it is a range, so you can take any value between this range. Okay, they have given the range. So to proceed with the numerical, you have to take any one value. So you can take any value between this range. Okay, so they have, in this numerical, they have taken it to be 0.20. 0.020. So if you take 0.021, or if you take 0.018 also, that will not be wrong. Okay, your answer will only, it will be varied from a little bit, difference will be there. That will not be wrong, because you are taking in between the range of you. Okay, so they are taking here 0.020. So now coming to the Now we have what we have to actually find out. We have to find out the area. Okay. Our aim first is to find the area so that we can find the breadth of the channel. Okay. And also we can find the depth of the channel. So to find the breadth and depth of the channel, first we need to know the area of the channel. Okay. So how will you find the area? We have the discharge given. Okay, so we know that the discharge equation is what? Q is equal to A into V. Everyone knows this, right? Q is equal to A into V. V here represents your horizontal velocity. Okay, since we are talking about the this like a rectangular chamber we are talking about. So here we are talking about your not the normal velocity, but we are talking about the horizontal velocity. So Q is equal to A into V, where Q is given, okay, Q in the question is given your 10,000 cubic meter per day. So you have to convert it, isn't it? It is in day. So first you need to convert it to meter cube per second. So for that you have to divide it by 24 multiplied by 60 multiplied by 60. This one is easy, everyone knows. So after you convert it to meter cube per second, okay, the charge you have got, now you can find out the area of the channel since your horizontal velocity value is already 0.3 given to you. The charge also you have got. So now from this equation, you can find out the area of the chamber. So that is your 0.385 meters square. Okay, so now after you got the area of the of the channel, now you can assume, okay, you can assume some while designing the designing a numerical, you can assume some of the things because every value is not given to you and you have to know what things you usually have to like assume. So for this sedimentation grid chamber of your designing process, so you can assume a water depth. Okay, what is the depth of the water? That means this is a capital H. You can denote it by capital H. So you can assume the water depth to be 1 meter. Okay, so the where is there, isn't it? The proportionating where is there. So from the crest of the where, so what is the height of the water there? So it is your 1 meter they are assuming. Okay, and that 1 meter of water, it is kept at, that is the crest of the where, it is kept at 0.3 meter above the channel bottom. So now we can find the width of the basin. So width of the basin is equal to like it is L into B is equal to area. Okay, here you see L into B is equal to area. So you have L, that is your height. We have assume it to be 1 meter. So 1 meter multiplied by your breadth. Okay, so from this equation we can find out your what is the breadth of the channel, that is 0.4 meter. Okay, so uh, next what they are finding, now you can they are finding the overall depth of the grid chamber. So overall depth will be obviously the water depth. Okay, the water depth which you have assumed. Then we have one 0.3, that is your the above the channel bottom, whatever depth we are considering, so that depth will also come. And also we have to consider one freeboard. So freeboard already I have explained in our previous classes. Okay, so this, if you are finding a depth, overall depth of a tank, so you have to add up all the depths that you are considering. So in this case you are considering the freeboard. Okay, then you are considering the depth above which you are keeping the crest of the weir, and also the water depth, okay, above the crest of the weir. So that is, we have assumed 1 meter, then 0.3 meter, and the freeboard we are taking it about 0.45 meter. Okay, so we are adding up all the depths and we got it to be 1.75 meter, which is the overall depth of the grid chamber. Okay, now you can find out, like, to find out the length of the this tank. Okay, you have a settling velocity. They have already provided the settling velocity in the question as your 0.02 meter per second. Okay, now we have one formula. This formula you have to remember it. That is the detention time formula. What is the detention time? This one also already been explained while doing the raw water treatment. Okay, you can refer to all those videos. So this detention time, it is your water depth in the basin is divided by your settling velocity. So water depth we have assumed it to be 1 meter, and settling velocity already given in the question is your 0.02 meter. So if you divide it, you will get the detention time as your 50 seconds they are getting. So now you find out the length of the tank. So length of the tank easily like you know this velocity into detention time. Okay, that is velocity into detention time. That is your horizontal velocity is 0.3 and your detention time is your 50 meter. That is your 15 meter. They are getting your length of the tank. Okay. So this is a this is 9.2a. Okay. So this is finally your they told to find out the channel dimensions. So everything you got, like you got the width of the basin, then you got the overall depth of the this basin, then you also got the length of the basin. So that is finally your numerical is solved. Okay. So another tough one. Okay. So now, okay. So next one we have your aerated grid channels. Okay, aerated grid channels we have. Just give me 1 minute. Let me see if I can find some uh, video of aerated grid channels so that it will be easy for you to understand. Just let me see. Give me a minute, okay? Oh, okay. I forgot to provide you the attendance link. I'm giving you one link in the chat box. Everyone fill it up, okay? See in the chat box whether you are finding the link. You fill this up, okay, during the class itself. After that, I will, at 12 p.m., I will close the link. Okay, no, I couldn't find any proper video which I could show you for aerated grid chamber. No worries, I will explain it. Okay. So this basically these aerated grid channels, they are also known as, or it is like your there is a spiral flow aeration tanks. Okay, they are known as your spiral flow aeration tanks, and they are having a detention period of 3 minutes. Okay, at the maximum there is your 3 minutes of detention time. So and this is it is of your rectangular cross section. Okay, and they are having a spiral circulation like that of an activated sludge aeration tank. And activated sludge aeration tank, we will be learning it in our next classes. And it is having a grid hopper. Okay, it is having a hopper. Okay, so it is having a grid hopper of like 0.9 meter depth, and it is having a sloping slides. Okay, it is having a sloping sides which is located under the air diffuser. So there is a air diffuser also. So okay, here you can see. So this is a hopper. Okay, this one you can see it is a hopper, and they are having some air diffusers. These are the spiral type of things. Okay, and this is the air diffuser assembly. So this is typical. This is a section of your this aerated grid chamber. Okay, so here basically the performance of this grid chamber, it is like that of a roll velocity and that of a detention time. And if the velocity, since it is having a spiral type of thing is there, so if the velocity of this the spiral or the roll, it is very high, so what will happen, the grid will be carried through the chamber. And suppose if the velocity it is low, then what will happen, the organic matter, they will settle down along with the grid. Okay, and what is the velocity, what is the roll velocity, that it is ranging between 0.15 to 0.45 cubic meter. And again, there is the detention time, already I told that for designing purpose it will be 3 minutes at the maximum flow. And for the length to width ratio is there. So while designing, all these values will be important to you. So if the length and the width ratio, it should range between 2.5 to 7. And also that width and depth ratio, it should be between 1:1 to 5:1. Okay, so basically it is aerated grid channel. So here air diffusers is there, so therefore the name comes that it is an aerated grid channel. And the detention period here, it is of the maximum of it is for 3 minutes. Okay, and also there is a hopper, grid hopper is there. So it is like a different type of your, like that is one is your horizontal flow type, and it is your aerated grid channels. Okay, okay, so there is one numerical related to your aerated grid channels. Okay, so let us see this numerical. So it is like design an aerated grid chamber for treating municipal wastewater with average flow rate of 0.5 meter cube per second. That is given in your MLD. If we talk in terms of MLD, that is your 43.2 million liters per day. So assume the peak flow rate to be 3 times the average. Okay, so it is given that you have to assume the peak flow rate to be 3 times of the average value. So peak flow rate is, since it is given, peak flow value is given to be 0.5 meter cube per second. And also it is given that you have to assume that the peak flow rate it is 3 times the average. That means you have to multiply the peak flow rate by 3. Okay, so after multiplying it, they are getting it to be 1.5 meter cube per second. Now you have to, since this is a aerated grid chamber, so you know that you can assume the detention, since the detention time is not given, so you can easily assume it to be 3 minutes. Okay, so assume the average liquid detention time to be 3 minutes, which is multiplied by 60, it is your 180 seconds. Okay, so now what is the aerator volume? So you have to find the aerator volume of the channel. So that is, if you multiply the peak flow rate and if you multiply the detention times, and you will get the aerator volume, which they got it to be 270 meter cube. So now if you have to, there are two chambers. Okay, so there are two chambers, but if you have to clean one channel, then you have to keep one channel at least in the working position. Okay, for that you have to first find out the volume of, since there are two chambers, so you can find the volume of one aerated channel. So how will you find it? You have to just divide it by 2, since there are two chambers. Okay, so what is the aerator volume you are getting? If you simply divide it by 2, then you are getting the volume of one aerated channel. So now if you find or if you determine, we have to determine the width of the channel and also the length of the channel. Okay, so if you have to determine the width of the channel, we don't know the depth of the chamber. Okay, we don't know the depth of the chamber, and also we need the width and depth ratio. We know that it is 2:1. Just now we have go through, isn't it? So if you find the width of the channel, we know that the width of the channel, the width depth ratio is 2:1. So easily from there you can find out the depth, that is your, it is, you are getting the width, you are getting it to be 6 meter. So finally you can find the length also. Length you already got, you got the volume, then you divide it by the this width and the depth, that is your 3 by 6, so it will be getting your 7.5. so width and length you have got. Okay, but generally what we do, whatever length we are getting for the design purpose, we generally increase a little bit of the length, or sometimes we increase a little bit of the height, for some conditions, for, and for, in this condition it is for your inlet and outlet conditions, we have to increase a little bit of the length. So you can just increase 20% of the length of whatever original length you are getting. You just increase it 20% and you are getting it to be 1.2. Okay, so if you multiply 1.2 multiplied by the length of the channel, so you are getting the the provided length. It will be your 9 meter. So you are using the two chambers. The one is your 9 meter, the other one is a 6 meter into 3 meter depth. Okay. Now, here, since in your aerated grid chamber, we are giving a air supply. Okay, so what is the air supply requirement? It is needed. So you can assume it to be like 0.03 meter cube per minute per meter length. It is adequate. So here it is. You can remember this value. Okay, it is 0.03. It is for a design purpose for your this aerated grid chamber. So this value, it is fixed. Okay, so what is the air requirement that you are getting? It is 0.03, that is multiplied by your whatever length is there. So for the whole length you are multiplying, you have need the air requirement, so you have to multiply with the whole length. So that is your 0.27 meter cube per minute. Okay, and also you have to find out the volume of the grid, whatever it is produced. So again we are assuming the what amount of sewage of grid is produced. So it is your 50 meter cube per million cubic meter of your sewage is producing daily. So you can find out the volume of the grid as your, this is the formula. Okay, peak flow rate of sewage multiplied by grid produced per meter cube of sewage. So if you multiply peak flow, that is your 1.5, and then you are multiplying the the grid as your 50 it's million liters, so 10 to the power 6. Again, the peak flow, you are converting it to second per day. So the whole thing, you are getting it to be 6.48. So the 6.48 meter cube per day, it is the volume of the grid that is produced daily. Okay. So this is about your aerated grid chamber. Okay. So next class we will be doing the detritus tank and all these skimming tanks we will be doing. Okay. So I hope everyone has understood, and if there is any problem in understanding, you can ask me later. Okay. If you go through once, I will share the PDF with you. After that, if you have any problem, you can ask me. Okay. So I hope everyone has filled up the form. Let me check. Okay, 26 responses have come. I will share the link once again in your WhatsApp group. And but after 12 p.m. the link will get closed. Okay. Okay then, everyone. Thank you so much. You may leave the meeting now.